All right, gang, more on the central limit theorem. Let me find an ink pen here. What I want to do, what my game plan here is the previous video that I just uploaded was on quantitative, well, if I can write here, trying to put this up without wearing my glasses, which could be a complete and utter disaster, but we'll see. So anyway, it dealt with quantitative data, and this is where you can think about it that the measurements that we collect are just numbers. And you know, the things that we've looked at IQs. I think we looked at head breadths. I can't even say that. I think we looked at heights, and so on and so forth. But in statistics, it turns out that the information that we collect isn't always quantitative data. Now, when we do, we want to think about those three things that I talked about in the previous video. We want to organize our data and examine the distribution shape. And we want to examine the appropriate measure of center. And we want to analyze the appropriate measure of spread. Now, what we've done so far, here recently, is we have focused on these distribution shapes that we call a normal distribution, where the appropriate measure of center is the mean and the appropriate measure of spread is the standard deviation. Now, all this stuff goes with quantitative data, okay? Quantitative numbers, measurements. But again, in statistics, we all quite often actually run into categorical data. Guys, categorical data, as you would think, let's just keep it kind of simple here. Let's just think about our class. What are some types of things that we could collect on students in Math 1500 that would be categorical? Well, obviously the first thing that comes to mind for me would be gender. Something else we may examine is political preference, maybe religious affiliation, favorite NCAA football team. I think I know what the overwhelming response there would be, Ohio State. Not me. I'm a University of Kentucky guy, but I know, a historically rich NCAA football team like Ohio State has a lot of fans in the state of Ohio. But anyway, guys, categorical variables take on different, just a completely different dynamic. First of all, distribution shape does not apply. Because if you think about it, when we construct a histogram, from small numbers on the left, whatever it may be, and as we go to the right, we get bigger numbers. So if we're sitting there looking at a bell-shaped and symmetric distribution, or if we're sitting there looking at a positively skewed distribution or a negatively skewed distribution, there's some sense of organization. Well, guys, it does not apply in categorical variables because the way we would construct the axis, the horizontal axis here, is irrelevant. For example, if we have, well, not irrelevant, but arbitrary. If we have political preference, for example, and let's just say we keep it simple and we do Democrat, Independent, Republican, and Tea Party. Trying to put these in alphabetical order so no one thinks that I'm, well, whatever. Although you may think there's a natural ordering on political preference, there wouldn't be in terms of creating a chart. So, I'm sorry, a table. So first and foremost, distribution shape is irrelevant. Secondly, the mean and the standard deviation cannot be calculated. Because guys, think about the mean. To have the mean, we need to be able to add our observations and divide by how many. Well, I don't know how you add a Democrat plus an independent and all that. I don't know how you do that. And standard deviation requires you to take a distance between an observation and the mean. So guys, these things aren't calculated either. So you might say, if everything that we've done so far doesn't work, what does work? Well, what works for categorical data? Is we express these things in terms of proportions. And guys, just as before, we can have a sample proportion. Now I say just as before, I'm kind of bouncing this off of the mean. Remember, we could have a sample mean and we could have a population mean. Well, it turns out here that we also can have a sample proportion and a population proportion. Guys, the notation for sample proportion is p hat. So it's p with a little caret on top. And it turns out that this proportion is found by taking x over n. The population proportion is just given as p, and it is calculated the same way with a little bit different notation. We take the count x out of the total to get the population proportion. Now this is much simpler than it may come across at first. So let me just make sure that we get this established. So let's say that in our class that we analyze gender, and it turns out that we have 18 males and we have 10 females. Now we can assume that this is a sample, which I think is reasonable. It's not a random sample, but it is a sample from Shawnee State University students. So we would use the notation p hat, and let's say, and I'm going to just use subscripts here, let's say the sample proportion p hat of the students who are males is going to be, again, x over n, where x is just the count over the total. Well, guys, we have 18 males, 12 females. Obviously, we have 30 students. So 18 would be 0.60, which can be equal to 60%. If we want to look at the p hat of females, same thing occurs, x over n, so the count over the whole. So 12 over 30 is 0.40, and which is equivalent to 40%. So guys, what you got to understand, it's an important thing to, kind of a hurdle to get over, is that proportions can come at you in 3 different shapes, forms, and sizes. Proportions can come to you, let's keep it simple. Let's just think about the proportion 3/4. That can come to you as a decimal, or it could come to you as a percentage. All of these are equivalent, and you've got to keep in mind that these things are equivalent, but they can be presented in the context of a problem differently, which makes learning more challenging. So guys, what we'll always try to do is we'll always try to get our p hat back into this form of using the decimal. So clearly, if we have the decimal, we can get to a percentage. If we've got the decimal, we can get to a fraction, and vice versa. All right. So guys, let's bounce this off of what we've talked about before with the central limit theorem. But I want to talk about, revisit the means, because I want you to start to look for patterns here. Okay. When I presented the central limit theorem for means to you in the previous video, I told you that we begin with a population, where the mean and the standard deviation are given. The next thing we do depends on the type of distribution that we're given. If we have a normal distribution, if this population we started with is a normal distribution, then this whole central limit theorem applies and holds true as long as the sample size is 2 or bigger. If it's not normal, then we have a little bit more stringent sample size restrictions. We need 30 or bigger. So guys, in our class, we tend to keep it simpler, believe it or not. And not normal to us just means skewed, positively skewed or negatively skewed. Now, there are a lot of different distribution shapes out there, but we don't study those in this class. The next thing I wanted you to understand is we set n and we take random samples of size n from our population. Now, just for speaking this problem through, let's say we decided that n is going to be 25. So we go into our population, pull out 25 observations, we add up their measurements, we divide by 25, we get our first sample mean of size 25. Throw those 25 people back in the mix, or 25 subjects, elements, dogs, cats, trees, whatever it may be, whatever we're measuring. Randomly select another 25 observations, add up their measurements, divide by 25. We get a second sample mean of size 25. Do that again, and you guys, you don't do this. What you imagine is that in theory you could do this forever. Well, you really couldn't do it forever, but imagine that you had some way just to exhaust all the possible random samples of size 25 from an initial population. Let's just say your population's all IQ scores. Select 25 randomly selected people. Measure their IQs. Add them up, divide by 25. We get an average IQ for the first 25 people. Throw those people back in the population. Pull out, randomly select another 25 people. Could be different. I mean, there could be an observations that repeated. Add up their IQs, divide by 25. We get a sample mean IQ for the second group of 25 people. Do that 3 times, 4 times, 1,000 times, 100 million times. Do that forever. What we end up with here in statistics is something very important. We call this the distribution of sample means x bar. Kick in the central limit theorem. Central limit theorem tells us, I'm going to abbreviate here. Central limit theorem tells us 3 very important things. It tells us that the distribution of these sample means, the histogram shape, will form a normal distribution. The next thing it tells us that the mean of these sample means will be equal to the mean that we started with way back here. And the third thing it tells us is the standard deviation of these sample means will be the sample, the standard deviation of the population, which we started with back here, divided by the square root of n. That's what central limit theorem tells us. Now, what I want to do now is I want to change this and what would happen if we examine this with proportions instead of means. So what happens if we change this and start thinking about categorical data instead of quantitative data? Well, we still start with a population, but our population now is described as a proportion, which we said earlier could be a fraction, a decimal, or a percentage. Now, typically, when we communicate levels of engagement, if you will, for a categorical variable, do we talk about fractions, do we talk about decimals, or do we talk about percentages? If you're going to talk about the proportion of students in your class who cheer for UK, would you walk down the hallway and say, you know what? We did a study today and 2/11 of the students in my statistics class cheer for UK. Well, you would sound like the biggest dork ever. Would you walk down the hallway and say, well, 0.217 proportion of those in my, I can't even say without laughing because it's so dorky, proportion of those in my statistics class cheer for UK? No, you'd say percentage. 22% of people in my class say they cheer for UK. This is the way we communicate. This is the way we work problems because it's easier to put in our calculator. But this is the way we communicate. So we're going to start out with a certain population, and we're going to communicate this with a population proportion, which will be given in a percentage. Now, I just told you that about 5 minutes ago, the distribution shape doesn't apply. We can't construct a histogram, so this normal, not normal stuff doesn't apply, and neither does this n greater than 2 and n greater than 30. Doesn't apply. What does apply is the following, that n times p and n times 1 minus p both have to be greater than or equal to 10. N will be our sample size that will pull out our population. P will be this value right here that we started out with. And 1 minus p, again, thinking about this p as a percentage, but it can be expressed as a decimal. 1 minus p is the value we got right here. And I'll illustrate that in a future problem. Okay? Now, next thing happens, set n, but let's say this time, say n's 100, because with categorical variables, we need a bigger sample size, okay, to make all this stuff up here happen. Now, we're going to take random samples, but guys, now we're not going to be taking sample means. We're going to be taking sample proportions. So we dive into our population, pull out 100 people. We ask them whatever question we're asking them, or measure whatever we're measuring. Let's say that 32 of those, 32 out of 100, the first 100 people we question. So my first sample proportion would be 0.32. I do that again. Create a sample proportion, the second one. That's determined by or calculated by the next 100 people, 100 subjects, elements, dogs, cats, trees, whatever, that have the characteristic that we're measuring. Let's say that we say up here, we say that 38% of people believe in ghosts. So we go in here and take 100 randomly selected people and ask them, do you believe in ghosts? And let's say that 32 did. Well, then this first sample proportion is 0.32. Take another 100 people out. Do you believe in ghosts? Well, 40 of those do. Well, then this is 0.40. We're going to expect variation here, as described by the sample, the standard deviation of the distribution of sample proportions. Guys, do this again. Do this again. And just like before, do this forever. Once we've done that, what have we created? Again, theoretically, we don't do this. We've created a bunch of sample proportions. So we call these the distribution of sample proportions. Not X bar, but P hat. Now, central limit theorem kicks in and tells us some cool stuff. And guys, I'm going to have a new sheet of paper for this. These sample proportions that we created by randomly selecting samples of size n, p hat 1, p hat 2, p hat 3 forever, right? Central limit theorem tells us three very important things. Again, what's important to know? The shape, the center, the spread. Always. That's what we're obsessed with in statistics. What's the shape? What's the center? What's the spread? Well, guys, the shape of these things is going to be a normal distribution. Once the shape of the distribution is defined as a normal distribution, what two things create a normal distribution? The mean and the standard deviation. Well, the central limit theorem tells us what those are. Now, before we called this mu sub x bar, but since we're looking at the mean of the sample proportions, we'll now call that mu sub p hat. Turns out this value is p, which is exactly what we started out with right here. The standard deviation, still known as the standard error, sigma sub p hat, is the square root of p times 1 minus p over n. Now, your brain is probably frying right now. You're probably thinking, Darbro's lost his mind. How in the world am I ever supposed to know that? Well, let's just go through a less theoretical example, and let's put some numbers here. 38% of people report that they in ghost. All right. First thing I know, P is equal to 0.38. This is my population proportion. Now, central limit theorem deals with sampling distributions. It deals with the distribution of samples, not populations. We start with the population given, and then we start examining how the samples behave from this population. Set in as 50. So let's just say, for example, that I go into my population, I pull out 50 people, and let's just say that they is adult Americans. Okay, so they here is adult Americans. So my population understudies adult Americans. So I pull out 50 adult Americans and I ask them, do you believe in ghosts? Each one of them. And I find out that 30 of them do. So my first sample proportion would be 30 out of 50, which is 0.60. Imagine doing that for all possible samples of size 50. What I know, what the central limit theorem tells us, is that the p hats that we create will form a normal distribution. The mean of the p hats will be equal to the p we started out with. And the standard deviation of the p hats will be the square root of p, which is 0.38, times 1 minus 0.38 over n, which is the sample size, which is the square root of 0.38. 1 minus 0.38 is 0.62. Now, if that's something, if you just don't have that ability to do that mental arithmetic, don't worry about it. It's not a big deal. Grab your calculator. It'll take you about 2 seconds. Put it in there and get 0.62. That's not a big deal. We have different strengths, ladies and gentlemen. Maybe that's not your strength. That's fine. It is my strength, but trust me, I'm sure you've got strengths that are my weaknesses. All right, so let's put this in our calculator. Guys, it takes a little bit of caution, but not much. So I want to take the square root of 0.38 times 0.62. Guys, don't divide it by a sample size of 50 and hit enter. So our standard error here is 0.0686. Now let me show the other calculator with the different operating system. Let me show it so you guys are, or if you've got a different type of calculator, how you do that. If you go second function square root on this type of calculator with an older, you'll see that you get a left parentheses. Now 0.38 times 0.62, a lot of people want to close up that parentheses. And I think it's because we've run into a situation with z-scores where you close up the denominator from the numerator. But guys, you don't do that here. You make sure that everything is typed in before closing up the percentage, or I'm sorry, before closing up the parentheses under the square root. So I tell the calculator that I want to take the square root of a bunch of stuff, and I want everything to have the square root, affected, if you will. So I tell the calculator that. Okay. Now, if you put in, I'll demonstrate that. So we get the same answer. Now, so I see this a lot when I'm teaching. I see students get just flat out get just sloppy, and they'll do that, and they'll get all tore up because they get the wrong answer, and then they just throw their hands in the air, and they're just like, "Well, I don't understand anything. I just don't understand why I do the same thing that you do on the videos, and I don't get the same answer." Well, no, you didn't do the same thing I did. You got sloppy. You put a parentheses there before it should be, and the calculator did what you told it to do, but you didn't pay attention to the detail when entering in your calculator. So, guys, that one's totally on you if you do that. Everything goes under the square root in the standard error for these types of problems. So guys, we got 0.0686. So what I know is the distribution of sample proportions. Will form a normal distribution. It'll have a mean of 0.38, and it'll have a standard deviation above the mean of, what did we say, 0.06. I'm just going to keep it simple here and round that off to 0.07. It's 0.06. So let's keep in mind here that this is really 0.0686, but I just rounded it 2 places. So 0.07 above this would be 0.45, and 0.07 below would be 0.31, and I could go on and put as many values of standard deviations above or below as I would like. So guys, before we saw that 68% of our observations in a normal distribution fall from 1 standard deviation below to 1 standard deviation above. So guys, taking 50 at a time, we would expect for about 68% of our samples to have between 31% of people and 45% of people who believe in ghosts. All right, gang. Let's get our hands dirty here. Let's work some problems. We got the tools to work just about whatever we want. But before we get into the new stuff, I want to make sure you're still okay with the old stuff. So right now we're keeping them separate. The next video we're going to start working problems, all tossed in together. So the first one says the weight of potato chips in a medium-sized bag is stated to be 10 ounces. The amount that they the amount that the packaging machine actually puts into these bags is normally distributed with a mean of 10.2, standard deviation 0.12 ounces. How do you know this isn't one of the new problems that I just taught you? Because it doesn't start out with a percentage. Those new class of problems, the categorical variable problems, the proportion problems, start out with a percentage. This starts out with a mean. So we know this is the old stuff, the stuff from the previous video. So what is the probability that a bag is selected at random is underweight? So guys, here's what happens. It's stated to be 10 ounces, so anything under 10 ounces would be underweight. I'll tell you what I'm going to do. I'm just going to use this one. So I would want to know the proportion of bags that are below 10. Make sure I got everything typed correctly. Yeah. So guys, about 0.0478. That would be the probability of selecting a single bag that is underweight. And that's pretty appropriate that it turns out that way, because I know in weights and measurement that, for example, you go in and buy a steak, and the steak says that, it's however big it is, or you buy a can of Pepsi or Coke, and it says 12 ounces. Well, guys, the filling machine doesn't get it perfectly on 12 ounces every time. There's variation in any manufacturing process. But these weights and and measurement people that work with our federal government and state government want to make sure that when you buy something and it tells you that you get a particular amount, that you actually do get the amount within some certain level of tolerance. And that's what they've set that at right here. Some of the chips are sold in bargain packs of 3 bags. If a bargain pack is chosen at random, what is the probability that the mean weight for the 3 bags is underweight? Now, this mean right here tells me what? Well, I got to do this central limit theorem. So I'm just going to go second function entry, because I know that the only thing that changes from taking a bag 1 at a time to taking 3 at a time and looking at the mean weight of those 3 is to divide out by the square root of the sample size. Now guys, a lot of times students will forget that division sign. I've seen that happen time and time and time again. I can't preach enough. You got to pay attention to detail. So the probability would be 0.0019. So guys, it is very, very unlikely, only about 19 out of 1,000 times, 19 out every 10,000, would you expect to get an average less than 10 if you buy something in 3 packs. Talk about these ultra bargain packs of 24 bags. What's the probability it's underweight? So guys, same thing, right? Instead of 3, we have 24. Same problem. And guys, it's not going to happen. If you get something like that, then there was a severe systematic flaw in the packaging process.